Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on November 7, 2025, about 4 days ago. And this paper tackles the memory wall in 3D Gaussian splatting, so a single consumer graphics card can handle huge scenes. The headline result is that the system, called CLM, trains scenes with up to 102 million Gaussians on one RTX 4090, while keeping quality high, and it cuts central to graphics processor communication by about 37 to 82%. The paper is titled, CLM, Removing the GPU Memory Barrier for 3D Gaussian Splatting, and the implications for scalable, high-fidelity view synthesis are quite significant. Alright, Figure 1 illustrates the novel view synthesis setup, where posed training photos teach a model to render an unseen viewpoint. The large background shows the scene, and the method aims to predict a new camera view that was never captured. The left and top right insets depict training images with known camera positions and orientations. The blue box at the lower right marks the novel view that the renderer must produce. So the previous figures set up the task. Table 1 now breaks down what each Gaussian actually stores. The table shows 4 attribute groups: 3D position with 3 numbers, covariance as scale and rotation with 3 plus 4 numbers, spherical harmonics color with 48 numbers, and opacity with 1 number, totaling 59. This breakdown matters because memory scales linearly with these attributes, which is why selective offloading and caching can bring huge savings. In short, most bytes live in color, not in geometry. Okay, Table 1 emphasizes where memory sits, and Figure 2 shows the end-to-end 3D Gaussian splatting training loop. The pipeline starts with all Gaussians, where Step 1 performs culling to choose only those inside the camera frustum. The middle block rasterizes that subset as Step 2 to produce a rendered image. A loss compares the rendered image with the posed ground truth, and Step 4, backpropagation, updates the Gaussians. Alright, Figure 6 lays out the training workflow that turns memory limits into a scheduling problem. The diagram shows 3 stages: frustum culling to pick in frustum Gaussians, order scheduling to cluster similar views, and microbatch pipelining to overlap transfers with compute. The dash panel illustrates 2 GPU streams and a CPU thread that run in parallel, so loading parameters and sending gradients overlap with forward and backward passes. This overlap is what trims communication time while keeping throughput high. So, Figure 6 covered the workflow. Figure 8 reports how far each system scales before running out of memory. The charts show 4 methods across 5 scenes, and the red bars for CLM stand tallest throughout. On RTX 2080 Ti, CLM reaches 47 million Gaussians on Big City, about 6.1 times the enhanced baseline and 2.3 times naive offloading. On RTX 4090, the right chart peaks at 102 million, roughly 5.7 times and 2.2 times respectively. So, Figure 8 showed capacity gains. Figure 10 now breaks down where GPU memory goes across model sizes and scenes. The stacked bars indicate model states versus other uses, and the red bars for CLM stay lowest, which prevents out-of-memory failures as size grows. In the rubble panel, both baselines hit out of memory, while CLM fits 45 million. In the Big City panel, model states dominate, so offloading yields even larger savings, and supports 102 million. Wrapping up, 2 takeaways stand out. First, clever offloading and pipeline scheduling let a single consumer graphics card handle scenes with on the order of 100 million Gaussians without sacrificing quality. Second, communication drops sharply thanks to caching and view ordering. The broader implication is democratized city-scale view synthesis on affordable hardware. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.